Hello all, welcome to Unit 2 in AP Chemistry. Unit 2 is called Molecular and Ionic Compound Structure and Properties. This is basically our chemical bonding unit. The beginning will just be an introduction to chemical bonds and is pretty much a review of Regents concepts. So a lot of this vocabulary is going to be quite familiar to you. I'm going to take you through this first lesson and then have you work on some sample questions together just to get started. So from the curriculum guide, the main points here is you want to apply knowledge of atomic structure, but now at the particle level, connect it to the macroscopic properties of a substance, which are the large scale properties. And also know that chemical and physical properties of materials can be explained by structure and arrangement of atoms, ions, or molecules and the forces between them. And also electronegativity can be used to help to make prediction of bond types. So we're going to look at how structure and arrangement is going to dictate function and interaction. The first four objectives or the first four topics of this unit are kind of linked together. I'm just going to go over the first one with you, but the overarching understanding that you need to have for the first four sections is that atoms or ions bond due to interactions between them, pretty basic. The first objective here is types of chemical bonds. So again, a lot of this is going to be a review of Regents chemistry. You will be able to explain the relationship between the type of bonding and the properties of the elements participating in the bond. Knowledge that you need according to the College Board Guide is that this is review from the last unit. Electronegativity values for elements increase going from left to right across a period and then decrease going down a group. When you have valence electrons shared between atoms, if they have similar electronegativity values, that gives you a non-polar covalent bond. So basically, if you think about identical nonmetals, that's going to be your non-polar covalent bond. So all of your diatomic elements, remember those, the Brinkelhoff elements, they come in sets of twos in nature. When a bromine bonds with a bromine or iodine bonds with an iodine, etc., they form a nonpolar covalent bond. Any carbon to carbon linkages in organic compounds, that would be a nonpolar covalent bond. If you have valence electrons shared and the atoms have unequal electronegativity values, that gives you a polar covalent bond. With a polar covalent bond, the atom with the higher electronegativity value, which you would be able to predict based on its position on the periodic table, that has a tighter pull on the electrons involved in the bond. That element would have a partially negative charge. It is depicted with this symbol. And then the element with a lower electronegativity, conversely, would take on a partial positive charge, like that. This is important. The greater the electronegativity difference, the greater the polarity of the bond, because that's a more unequal distribution of the electrons in that tug of war. And the thing you need to remember is that all polar bonds have some sort of ionic character to them. Bonding is a continuum. There's no cutoff of where polar covalent bonds end and where ionic bonds begin. Same thing where like the non-polar to polar line. So it's kind of a spectrum where if you have identical electronegativity values, it's non-polar. And then if you have a great electronegativity value, it's ionic. But like the lines where non-polar and polar begin, or when polar and ionic begin, they're blurry. There's no set cutoff in the difference of electronegativity values. There's different sources will give you different values, so nobody teaches it that way. Generally, if you have a metal and a non-metal, you have a great disparity in electronegativity values. That's an ionic compound. If you have two non-metals bonded together, it will either be polar covalent or non-polar covalent. The best way to examine this is by going through the properties of those substances. When you're dealing with a metallic solid, we'll talk about metallic bonding, the valence electrons are delocalized, meaning they're not isolated in place. They're floating around the whole surface of the metal. That's that sea of electrons concept we looked at in Regents chemistry. So a chemical bond is a force that holds groups of atoms together, makes them function as a unit. A bond will form, and we'll talk about energy in the next lesson. A bond is going to form if the energy of the group is lower than that of the separated atoms, because tendency in nature is to reduce the amount of energy in a system. There are three basic types of bonds. I'm not sure why these two images are kind of transparent. Sorry about that. So you have ionic compounds. So this says magnesium oxide, potassium dichromate, nickel 2 oxide, which is electrostatic or positive negative attractions between ions. You have covalent bonds, which is the sharing of electrons, and then you have metallic bonds where you have the mobile valence electrons attracted to the positive nuclei that make up the whole system. For ionic bonds, key vocabularies: transfer of electrons. Remember, it's the metals and the non-metals. For properties, this is memorization. This is the part in Regents Chem that everyone's like, I will immediately forget this information. You need this information. Ionic substances have very high melting and boiling points. Think table salt. If I throw table salt in a skillet on my stove and come back, it'll just be hot salt. It's very difficult to melt, very high melting and boiling points, which indicates strong bonds. Some ionic compounds are soluble. They will conduct electricity as a liquid or if they are dissolved. Okay, so a solid ionic compound like salt, if I stuck a conductivity tester on it, it would not conduct electricity. But if I dissolve it in a soluble ionic compound in water, it's an electrolyte. It will conduct electricity in solution. If I took salt and did melt it down, raise it to a very high temperature, hit its melting point, those ions are moving now, they can conduct electricity. Most ionic substances are solid. For properties, most are soluble in polar solvents. They conduct electricity. This is, again, kind of reiterated, only when molten or dissolved in a polar solvent. This is because the charged particles are free to move, and the higher the concentration of ions in the solution, the higher the conductivity. These tend to be brittle. I don't know why I have the picture here and not the statement, but they're brittle. The reason why is because if you put a force upon these ions that are originally arranged in this alternating positive-negative pattern, you shift their positions and you would now align like a negative with a negative and a positive with a positive. Those like charges repel and it will split apart. So if you had like a chunk of rock salt, you could split it apart easily because they're shifting the ions. These diagrams just show you why it would not dissolve as a solid, but it can dissolve when it's molten, melted, or dissolved in water. Both of those show the same thing. They have crystalline structures. If you take advanced level chemistry courses in college, bless you, you'd have to learn the different shapes of the crystals and things. You do not need to know that for this class. Next up, we have metallic bonding. So this delocalized, I want you to understand what that means. So localized means that the electrons would be isolated in one place. Delocalized means that they're not. The valence electrons are free to move across the surface of the entire element, the entire metal, and kind of float around. Metals tend to have high melting points and boiling points mostly, but you can melt them down. Gallium is a metal that can actually melt at your body temperature. Metals do not dissolve in water. They will always conduct electricity. And then your luster, malleability, right? Shiny. Malleable means you can mold it and shape it. Ductility means you can make it into a wire. For covalent substances, you have a sharing of electrons. You're going to be dealing with nonmetals. They tend to have lower melting and boiling points as compared to ionic substances because they have weaker forces of attraction. They tend to be insoluble unless they are polar or asymmetrical in shape. We'll talk a lot about molecular shape in this unit. You're going to be drawing molecules in your sleep. They do not conduct electricity because they do not have charged particles. And anytime you see the word molecule, immediately you have to associate that with a covalent bond. So this section here is just for you to practice identifying if something is ionic, metallic, covalent, or both ionic and covalent. In the video, it's going to pause and just give you a few of these to practice. Okay, so next up, this is just wrapping up this little section. When you're dealing with covalent bonding, this is just the diagram. This non-polar covalent bond is equal sharing of electrons. If the two nuclei are identical, they have equal pull on the electrons involved in the bond. So here's, the last one was hydrogen. This is a fluorine molecule. This region is of electron density is where the bonded electrons would be. If you have unequal sharing of electrons, so not enough for one element to totally rip the electrons off of the other element, but just so there is a disparity of attractive force, the bond would then be polar. Where's my pointer? Come on, whoa. The bond would be polar and electrons would be pulled toward the more electronegative atom. So you need to be able to predict trends in electronegativity to tell which side would be slightly negative and slightly positive. You would have this asymmetrical distribution of charge. The region is called a dipole. So this example here is hydrogen fluoride. Fluorine is far to the right on the periodic table, so it has a higher electronegativity value. So the electrons in this bond would have a greater pull towards the nucleus of the fluorine than they do towards the hydrogen. So the hydrogen side would be partially positive, the fluorine side would be partially negative. Fluorine has the highest electronegativity value of any element. We will talk about polarity of molecules later when you learn the shapes. So if you do end up with an entire molecule being polar, it will have a slightly negative and slightly positive charge. The more polar the bond, the greater the polarity of that region. And if you do have a polar molecule and apply an electrical field to it, the molecules will actually arrange themselves so that the negative side of the molecule is facing the positive portion of the electrical field and vice versa. So I know this was a very quick introduction, but a lot of that is background knowledge. It's important for you to be able to distinguish between formulas when they are ionic covalent or metallically bonded. It's important for you to be able to tell if a bond is polar or nonpolar covalent, characteristics of substances that contain covalent, ionic, and metallic bonds as well. In the next section, we're going to talk about energy. I'm going to teach that live because I want to make sure you have the opportunity to really digest this info. Thanks for